Hello and welcome. In this video we're going to take a look at what is probably everybody's least favorite kind of function, and that's inverse trig functions. Now we have to take these trig functions that we've already looked at and try to figure out how we form the inverse and figure out why we even need the inverse. So why don't we start off with the most common, I guess, trigonometric function, sine x. And so here's what the graph of sine x looks like. Now what we would maybe be using an inverse trigonometric function for is to figure out, what value of x do we need in order for sine x to equal something. So, for instance, if we had something of the form sine x equals 1/2. Now we've got an equation where x is unknown, but we know the result of applying sine to x produces the result 1/2. How do we undo that? Well, first of all, it's actually a common triangle. Sine x equals 1/2. You may already know an angle, and that would be pi over 6. And that would be one value that's possible, and that's be somewhere around here as pi over 6. And we know that at that particular value, sine of pi over 6 is 1/2. And that would be corresponding to a triangle in the first quadrant. And we also have another triangle in the second quadrant, and that would be, if a triangle is formed in this orientation, then the angle from 0 all the way into quadrant 2 would be 5 pi over 6, and that would be over here. And there's just two values, but if we actually take a look, and I have not drawn this at all to scale, you can actually see that there'd be sort of infinitely many places along there where it equals 1/2. Now that means that sine x is not a one-to-one function. Whenever you have an equation, sine x equals a value, you might have infinitely many solutions. So we would actually maybe say that the solutions to this would be x equals pi over 6, and x equals 5 pi over 6, and then you take either of those answers and add any multiple of 2 pi to it. So we could say plus 2n pi, where n is any integer. Now, in the case that you may have something of the form sine x equals 1/3, then that's not a special triangle, and now you're going to have to try to approximate the value of x, and that's where inverse functions are going to come in quite handy. Now, you can't actually find the inverse of a function that's not one-to-one, so let's see if we can somehow take this graph and transform it somehow into a graph that is one-to-one. Now we have to be a bit destructive here. The only way we're going to make this one-to-one is actually by getting rid of a lot of the actual graph of sine x. We're going to restrict the domain to one short piece of sine x that will have n points, but not the entire function. So just a function that goes as far as pi over 2, and this would be the point pi over 2 comma 1, and goes as far backwards as negative pi over 2 comma negative pi over 1, or negative 1. And that would correspond to simply quadrant 1 going in the positive direction, but we'd also have quadrant 4 because this is actually traveling backwards, and that'll give us in the negative direction an angle in quadrant 4. So we've just basically taken the restricted sine function. The restricted sine function would be sine of x, where x is in the interval from negative pi over 2, pi over 2. And by choosing that particular interval, we still have a function that goes from a y value of -1 to a positive value of 1. So that covers the entire range of the full sine function. It just restricts it to only two quadrants. And one quadrant would be a negative angle, resulting in a negative value of sine x. And the other quadrant would be a positive value x, and that results in a positive value of sine x. Now we can start making the inverse function of that. There are two ways that we can write the inverse of sine. The inverse sine function can be written as sine with the inverse symbol -1 of x, or, because that notation kind of looks like an exponent but really has nothing to do with exponents, it can also be written as arcsine. Now my preference is using arcsine because that is at least something that you can type in on a computer and it recognizes that as a function. Whereas most of the time, if I try to put sine with an exponent of -1 on there, computers get pretty confused. Rightfully so. It does look like it's just going to be 1 over sine, and that's not the same thing. The inverse sine function is defined so that if you have arc sine of x equal to y, that's equivalent to sine of y equals x. So they are inverses of each other. They completely undo them. One cancels the other one out for the most part. Now, if we're using the restricted sine function, it has a domain from -pi/2 to +pi/2, and gives us a value between -1 and 1 for the range. So arc sine, since it's the inverse of that, will have a domain from -1 to +1 and has a range of -pi/2 to +pi/2. So keep in mind that things like arc sine of 3 are undefined because it's not in the domain. Arc sine of x needs to have x between -1 and 1. And also important is no matter what value between -1 and 1 you plug into arc sine, it will only give you angles from -pi/2 to +pi/2. Those would be angles in quadrant 1 and 4. Okay, now that we've got arc sine defined with domain and range, we can go back and we can actually try to do something like evaluate arc sine of 1/3. Now, if you want to, you can start to imagine which quadrant this has to be in. Now, to figure out which quadrant it needs to be in, because we have arc sine of 1/3, that means that sine needs to be positive in this quadrant. And that's only going to happen in quadrant 4. So we already know that this is going to be an angle in radians in quadrant 1. And you can evaluate this on a calculator and see what you get approximately. And we get something like 0.339. Now in radians, if you think about pi being 3.14, that would be halfway around the circle. And half of pi would be half of 3.14, so that's about 1.57. And if you have a number between 0 and that, we're in quadrant 1, so that would be what we'd expect. We are in quadrant 1 right now. And in terms of maybe drawing a triangle, you can take a look. We'd have a triangle in quadrant 1 where the opposite side would be 1 and the hypotenuse would be 3, and the angle in here in the middle would be 0.337. Sorry, 0.339. All right, that leads us back to solving the equation sine of x equals 1/3. Sine of x equals 1/3 has the solution 0.339. And if you actually round that, it ends up being 0.340, because actually the number after the 9 is an 8. But essentially, it's this terrible number. You can make that rounded as much as you need to. But that's actually only one solution. There's many solutions. And that's because if you think about this, this is an equation involving sine, not the restricted sine function. So going back up to our example of sine x equals 1/2, we saw pi/6 in quadrant 1, 5pi/6 in quadrant 2, and then every time we go around the circle, we get additional solutions. So this isn't the only one. It might be useful to draw some triangles in the corresponding quadrants where sine is positive. We've got one triangle already. And then you can take another moment to think about where else we'd be able to form a triangle that has sine being positive 1/3. And you'd have to make sure that y, the vertical, is still positive 1. So that would have to be over here in quadrant number 2. Now the angle inside that triangle is also 0.339, or 334 if you wanted to round that. But what is the angle from standard position 0 going around? Well, one way you can do that is take pi minus 0.339. So our next value of x would be half the way around the circle minus 0.339, which if you see from the picture kind of makes sense. And that is also approximately 2.801. And again, that also rounds because it's 2.8017. So that would round up to 2.802 approximately, depending on how many decimal places you need. You may want to keep multiple decimal places or store this on your calculator so you have that for reference. And now that you've got an answer in quadrant 1 and an answer in quadrant 2, you can then add a multiple of 2 pi to each of these. So overall the solutions would have to be, and let's go with 3 decimal places, 0.340 if you're going to round up, plus any multiple of 2 pi, so we call that 2n pi, and then rounding the other answer up, 2.802, rounded up to 3 decimal places, 2n pi would be any multiple of a circle afterwards. And that would actually be infinitely many solutions because sine x is not one-to-one. Benefit of restricting the domain here, the benefit of restricting the domain is that so we can get a function on our calculator where you can just pop in inverse sine and it gives you a number. You can't have a function that's not one-to-one and still have an inverse. So we just force it. That at least gives you one answer, and then from there you can calculate all the other ones. What about cosine next then? Well, looking at the graph of f of x equals cos x, it's apparent that this is also not a one-to-one function. But again, we're going to force it to be a segment of cos x, take that restricted domain so that we end up with a one-to-one function and then take the inverse of that. So we start hacking and slashing here a little bit, and we're going to look for a segment where it passes the horizontal line test. But this time we're not going to take a segment from negative pi over 2 to positive pi over 2. We're going to take a segment from 0 to pi. And this produces a one-to-one function. It passes the horizontal line test in this case. So now we can go ahead and say, well, this is a restricted domain from 0 to pi, and we can define inverse cosine. And again, I kind of prefer the arc cos option here, but you can go with cos to the -1, and most calculators will show you that way because it fits better on a button. Now, what is the domain and range of the inverse cosine function? Well, seeing that the domain of the restricted cosine function is 0 to pi, and that gives us a result from -1 to +1, that means that the domain of arc cosine is -1 to +1, and it has a range of 0 to pi. And 0 to pi correspond to quadrants 1 and 2. So we're going to get angles in quadrant 1, and we're going to get angles in quadrant 2 this time. Those are the two types of angles that we need. And in quadrant 1, cosine of x ends up being positive, and in quadrant 2, cos x ends up being negative. And then we can basically plug any value from -1 to 1 into the inverse cosine function and find a corresponding angle in quadrants 1 or 2 with that value. Now, for instance, if we wanted to look at arc cosine of -3/5, that would be allowed because -3/5 is in the domain. It would be between -1 and 1. And we can plug that into a calculator and see what we end up with. And right away we see that we get a number between 0 and pi. We end up with 2.214, so on and so forth. Now we know that that is less than 3.14, so it's less than pi. And it's more than 1.57, which is half of pi. So that puts us in quadrant number 2. And that's kind of what we'd expect because that's the quadrant that we're looking at here where cosine ends up being a negative number like -3/5. So that will give us at least one potential place on the 4 quadrants where we have cos x equal to -3/5. And that's in the case over here where we have a -3 being the x and 5 being the hypotenuse, and the angle from 0 measured over would be 2.214. Now just keep in mind something like arc cosine of 5, well, that would be undefined because nowhere around any of the 4 quadrants can you find cos x equal to 5? And so this would be undefined. That is not in the domain from -1 to 1. Now, while all 6 trigonometric functions, sine, cosine, tangent, cosecant, secant, and cotangent, all have inverse trig functions that go with them, we tend to focus on arcsine, arccosine, and arctangent. And what might be a little surprising is that arctangent is going to be probably one of the ones that we end up using the most in calculus, particularly if you are going on and taking a second course in calculus all on integrals. And we'll see that that's actually a pretty nice function. It is in many ways a nicer looking function than arcsine or arccosine, even though tangent isn't that great of a looking function. Now let's see if you can remember what tangent looks like. Now the thing about the graph of tangent, or f of x equals tangent x, is that it has asymptotes. It has these values where tangent is not defined. And that happens, if you're thinking about the unit circle, at the top and bottom of the unit circle. So the top of the unit circle is pi over 2, and the bottom of the circle is 3 pi over 2. At least if you're heading in the proper anti-clockwise direction. But if you're heading in the clockwise direction, then the bottom of the circle can also be thought of as negative pi over 2. All right, so those are some asymptotes, and you can see this weird behavior there. But again, tangent x is not a one-to-one function. So what do we do to make this a one-to-one function? Same as before, we just chop away some pieces. Might as well actually use the eraser here. Let's just get rid of the parts that don't work for us. And let's see if we just chop away some of the other quadrants except for quadrants 1 and quadrant 4. Now in quadrant 4 we're actually going in the negative direction. We end up with a one-to-one function now. Quadrant 1 and quadrant 4 traveling in the negative direction. It's a one-to-one function. Now unlike if I scroll back up here to cosine x and sine x, I have solid dots at either end of the restricted domain, but in this case I have asymptotes at either end of the restricted domain. The restricted domain in this case is going to have to use round brackets. If we restrict the domain of tangent to just negative pi over 2 to positive pi over 2, but not including those numbers, surprise, it actually ends up becoming a one-to-one function, and we can define the inverse tangent function. Now, if you want to think about the domain and range of arctangent, just because that's the way I like to use, then we can go ahead and reverse this. Because we've restricted the domain of tangent x to negative pi over 2 to positive pi over 2, that's going to be the range of arctangent of x. But what is the domain of arctangent of x? Well, looking at this blue curve that comes from tangent, if we restrict that, it actually, you can see it ends up going down to negative infinity, and it goes up to positive infinity, and it covers the entire y-axis. And so the domain of arctangent x is all real numbers. And that makes this kind of one of the nicest inverse trig functions, is that you can take arctangent of any number you like, but it will only ever give you a value from negative pi over 2 to positive pi over 2. Just for an example, we can do arctangent of root 3. Now root 3 is definitely bigger than 1. If we tried arcsine of root 3, it'd be undefined. If we tried arccosine of root 3, it would be undefined. But arctangent has a domain of any real number, and we can compute arctangent of root 3. Now for this one, let's see if you even need a calculator. You might even try to figure out what this is using some special triangles, because we have special triangles involving root 3. You could write this as arctangent of root 3 over 1 to make it a fraction, and then that'll help you figure out what quadrants it's in. Remember that arctangent of a positive number, we're only looking for angles in quadrants 1 or 4, so it had better be in quadrant 4 if you want it to be positive, with an opposite side of root 3. and an adjacent side of 1. And I haven't drawn that to scale. It's going to probably look a little better if I actually try to make it look more to scale. And what's that angle? In quadrant 1, that angle is pi/3 because it's a special triangle. And there you go. That's how you can use the arctangent function in order to reverse the operation of taking tangent of an angle. Now, last thing here to cover about arctangent is its graph. Surprisingly, we actually might need this later. The graph of arctangent is simply, by properties of inverse, a reflection of the graph of restricted tangent over the line y = x. Now, because I've got a computer here, that's going to help me out a lot. Now, if we take the graph of tangent and then we try to slap on the line y = x here at 45 degrees, or a slope of 1, then we can try to take the mirror image of it over that line. Now, of course, because I'm using a computer, I'm going to cheat, and I'm going to start flipping this thing. And after we flip it, we end up with this green graph. Now, remember that the blue graph has asymptotes at pi/2, and another asymptote here at -pi/2. So now this new graph is actually going to get closer and closer to, well, we'll see this later here, a horizontal asymptote of pi/2. It's going to get flatter and flatter as we go, and it's going to go out to -infinity out the left-hand side and get closer and closer to -pi/2 for its y value. So in the end, the blue curve we can get rid of, and then take a look at the overall shape of our arctangent function. And there you go, it has that kind of shape. It's very similar to the tangent graph, but because it's been flipped over a diagonal line, those vertical dotted lines are now going to become horizontal dotted lines. All right, well, that kind of gives you a little bit of a basic inverse function kind of know-how. We're going to be focusing on inverse sine, inverse cosine, and inverse tangent in order to solve equations using sine, cosine, and tangent. And we're going to be looking at arctangent, especially as kind of this interesting function that has a domain of all real numbers, but it actually only has a range from -pi/2 to +pi/2. It has these weird behaviors at both ends. So it's good to have all of this kind of in mind for future topics. Well, thanks for watching, and I'll see you guys in the next video.